Consider there is a bridge like this. There are two supports at two sides of bridge. And there is a load moving on this bridge. It could be motorcycle, pedestrian, vehicle, etc. So this is the load. As you know, this is a moving load. So I write moving load because you know the loads, the vehicles on the bridge are moving. So basically they are not statics, as you already learned, because you are used to solving problems when the load doesn't move. So this is a bridge and this is a moving load. And you are going to design this bridge as a civil engineer. So you want to know as a civil engineer if this is support A, it has a reaction at point A, it has a reaction at point B, and because usually we don't have a horizontal force applied on the bridge, the horizontal reaction at point A is considered zero. So now the question is how the amount of RA is changed when this moving load is moving on the bridge. This is the question. So now determine RA, so I put a question mark, when the load, let's say this is, for example, 5 Newton load. When the load moves on the bridge, so I'm trying to just start nicely because the first break in this chapter is important. You need to understand the meaning of inference line. Consider the moving load is right on the axis of reaction, support reaction. So we have the moving load here, we have the support reaction here, we have support reaction here. How much is RA in this case? Yes, you can write sigma fx, sigma fy, and from the equation sigma fy, you can find RA, which is 5 Newton upward. I just put it inside the margin. We are done with it. Is there any question? It's quite simple. Now, the load moves right in the middle of the bridge. And the length of bridge, let's say, how much is the length of bridge, Braden?
10 meters.
10 meters, very short bridge, okay. So, if the load is right in the middle, then we have 5 meter, 5 meter. This is RA. This is RB. So I forgot to tell you that in first case, but we don't need it. Okay. So now, how much is RA in this case? Remember, this is a symmetric figure. So you don't need to use equations of equilibrium. You can just give me the answer. 2.5. Because it's symmetric. If it is not symmetric, then you can write equations sigma and sigma x. So here, RA is 2.5 Newton upward. So I put it in a margin, in the box, so we know this is the second case. And then, again, the load moves to the left, exactly at the end, right on the reaction B. So this is RA, RB. Now, how much is RA? 0. So in this case, RA is 0. So basically we have 3 boxes. And we calculated the amount of reaction at point A when the moving load, which could be, for example, Braden, is here. Braden is in the middle of the bridge. Brendan reached to the end of the bridge. You can see the amount of reaction at point A is changing from 5 to 2.5 and then eventually to 0. I think you understand this because it's not complicated. So now we want to put it on a diagram. I just use this part. This is the bridge from A to B. How much was the load at the beginning, RA? It was 5. So I say if the vertical axis is showing the amount of RA and the horizontal axis is X, then RA is 5 here. Right in the middle, it is 2.5, and then once we reach to point B, it is 0. 5 Newton, 2.5, 0. And I just connect them together with a straight line. This diagram is the inference line for RA. If you understand this concept, you will be comfortable in this chapter. If you don't place the first break and don't understand the concept of inference line, you will be facing problem. So now you can ask question. So if somebody asks you to draw the inference line for RA, then this is this diagram in red color is the answer. The diagram in red color is the answer. So I write influence line, but when it comes to influence line, it must be about a variable. The variable in this question is RA. So we are drawing the influence line for vertical reaction at point A. So we have a vertical axis, which shows the amount of RA. We have a horizontal axis, which is along the beam. And then we have a red color line, not a curve, which is inference line. So the red color line is inference line. This method is called tabulating. So the textbook basically spends a lot of time and asks you to solve a lot of problems using this basic method. It means you just find the points and connect them together. Easy. So this is called tabulating. So we should not spend much time on it because it is easy, but it is very time consuming. And it is not actually the focus of this chapter. We are going to use the Mueller method. We will learn it later. Based on the Mueller method, we don't need to calculate these values when it comes to a complicated structure, not a simple beam like this. My question is why we connect them with a line. Let's try this. Why we use a line to connect RA for point A, B? Why we don't use a curve? The answer is when the structure is determinate, for determinate structures, the inference line is always linear. Always linear. So I write IF, inference line, is linear. And you know what structure is determinate. You already practiced the law and it is part of your exam 1 October 1st. So if the structure is determinate, doesn't matter it is a beam or frame, etc. The inference line is a straight line. So you just need to find some of the points and connect them together. The main focus of this chapter is determinate structures. That's it. So this is the concept of inference line. And you will face challenge later because you will forget this concept. So whenever you have doubt about something, just remember this concept and recheck your solution. Now, the situation is actually more than this. As a designer, you want to find the reaction at point B when the moving load is moving, and then you want to find how much is the moment at point right in the middle of this. Let's say this point, I call it point C, or maybe you want to know how much is the shear force at point D when Braden is moving on the bridge. So you need to draw the same diagram, you need to follow the same tabulated data, the same process to draw the inference line for shear force at point D, for shear force at point D, or maybe, so these are shear force, maybe bending moment at point E, etc. And I am sure you can find these values. I'm sure you can find shear force at point D. These are very simple. Sigma fx, sigma fy, sigma m. You can find bending moment at point E, and then you can connect them together. As a designer, you want to know, you want to go one step further. Which of the shear force at point C, D, E, F, G, H is the maximum when Braden is walking on the bridge? That would be more complicated, because you cannot draw the inference line for all of them. So these are the concepts that we are looking for in this chapter. We want to know if there is a concentrated load on this bridge, how much is the maximum bending moment on this bridge? Doesn't matter, point A, B, C, D. We have to identify that point. How much is the maximum shear force? And sometimes Braden goes with his friends. So there are a bunch of concentrated loads. In that case, how to find the maximum bending moment shear force? You can see it is more complicated. And sometimes he is driving his car. So it's a uniformly or maybe non-uniform distributed load. It's not a concentrated load. So these are all the concepts we are looking in this chapter. Yes?
So it remains true that we use a line even if it's non-concentrated loads?
If your structure, your answer is there.
Okay.
So Peter must answer Braden's question. Braden said, if the load is not a concentrated load, can we still say the inference line is linear?
Sure.
Yes, because if the structure is determinate, then the inference line is linear. It has nothing to do with uniform load or concentrated load or distributed load, etc. Okay. There are some methods when the structure is not determinate. Qualitatively, we can draw the inference line, and I will try to include that if we have time for indeterminate structures. Okay, so now your mind is ready. I hope you understand the concept of inference line, because I'm not used to explain a lot in the class. I'm just used to do the calculation, but I want to make sure you understand the concept, because we have maybe 5 or 6 sessions, or maybe 7 sessions working on this concept. So now, let's start with the first example. Okay, I'm going to erase this part. The simple question said that we have a beam. So we have a beam from A to B. The support reaction is roller. So point A is a roller, point B is a pin support. The length of the span of beam is L. The question is asking you to draw the inference line for support reaction at point A. So IF, I am personally using IF, but you don't see this acronym in the textbook. So actually it's not an acronym.
It's length L.
It's inference line. But to save the time, I just write IF because I don't want to write IF a lot of times on the board. So inference line for reaction at point A. The first step is place a unit load, because in this question we don't have any load on this beam. Basically you are not given any load. In general, when the question asks for inference line, there is no load on the beam. It means the load is just an arbitrary load downward moving on this beam. So you need to place a unit load downward on the beam. So if you have the diagram for a unit load, you multiply it by the self-weight of Braden, then you have the inference line for Braden. Or if the load is 1 ton or 10 ton, you just multiply it. This is the reason we use a unit load, because you can multiply by any value later. So this is the procedure. You always place a unit load and it is always downward. The sign convention is positive upward. So sign convention for the unit load is assumed to be positive when it is upward. This is just a sign convention. So now we do it. We have a unit load at point A downward. Second scenario, we place the unit load right in the middle of AB. And the last case scenario, we just place the unit load downward at the end. The span of the beam is L. So if you calculate the reaction at point A, is 1 here. Reaction at point A is 0.5. We don't use a unit. The unit could be Newton, pound, kip, etc. And reaction at point A is 0 here. Similar to the previous one, we just connect these points. 1, 2, 0.5, and 0. So this is the inference line for RA for this question. So we are still using the tabulated method. It means we place a unit load and then we calculate the amount of that variable, which is reaction at point A in this question, and then we connect them by a straight line. And we will solve a couple of examples in this way, because I want to make sure you understand this concept. Because once we move to Mueller method, you will forget this method. I promise you. So try to keep it in your mind. This is the definition of inference line. Next problem is a bit more complicated in terms of calculation. So let's see. there is a frame. So I draw it here. We have a fixed support, we have a pin at point B, and we have a pin at point C, pin support here. We have a slider or shear hinge at point D, linear spring E. So the question is not asking for drawing the inference line. The question is asking to find the height of inference line. So I just write here, determine height of inference line. So I use IF just to save the time. At right side of shear hinge. Shear hinge D. Let's start with this. This is the first part of the question. So basically you don't need to draw the inference line for the entire beam. It says we just need one point out of that inference line, and that one is the right side of the shear hinge. It means the red color inference line in previous example, we don't need the entire red line, we just need one point of it, and that point is the right side of the shear hinge. So now I'm still taking you into the concepts. So it means, because Clement is looking weirdly, I guess. So if for example, this is the inference line, the question is asking only this value. How much is this value at the right side of D? That's it. Okay? So now, how to solve it? What method do you propose? You already know the concept of inference line. And in previous example, you learned how to find the amount of inference line for different points. Remember, you found inference line for point A, B, C, they connect them together. So now you just need to find the amount of inference line for point D. So what to do? Where should I place the unit load? Remember, we have to use a unit load, and we have to place it right at the right side of D. So this is the method. We place a unit load downward at the right side of shear hinge, because the question is asking for that. And it makes difference if you place it at the left side of the shear hinge. Okay, now this is just statics. We have a structure. The load is 1 maybe Newton. We don't care about the unit. And it is placed at the right side of the shear hinge. And then what are we looking for? In this structure, a unit load is moving from A to E. Determine the height of inference line of reaction C. So basically, the height of inference line, so let me revise it. At RC, so basically you need to find the reaction at point C. I put a question mark here. At right side of shear hinge D. So you need to find the amount of RC. We are going to draw the influence line for RC, but just the point of that at the right side of shear hinge. So the unit load is placed at the right side of shear hinge, and then we need to find RC. That's it. So basically, the question should ask you to draw influence line for RC, but it doesn't. It says instead of drawing the influence line for reaction at point C, just give me one point out of it, and that point is the right side of shear hinge D. It means you need to place the unit load at the right side of D. Any question?
Would it be 0?
Yeah, we will discuss it, but did you understand this? Okay, so how is it 0? Because this from now we are going to discuss statics. So how do you say 0? What?
So the shear hinge doesn't carry a shear load across on the right side of D.
The shear hinge yes, the shear hinge doesn't carry the load, but do you agree this unit load will be transferred to the spring? Because as you said, the shear hinge doesn't carry the load. So we will have a reaction for the spring, etc. And we will see if that will affect RC or not. So let's look at the free body diagram. That would be helpful. The dimensions are in this way. From A to B is L, from B to C is L, from C to D is L, and my apology, my drawing wasn't to the scale, so just extend this because the distance from D to E is 2L. Okay, I'm going to draw the free body diagram for different segments. Segment AB, if I have segment AB, I have just a shear force at point B, and for the reaction RC, I want to consider it downward, but it is up to you because later you will find it. The shear force at point B is upward. I have a moment at point D because shear hinge will carry the moment. So we have a reaction at point E, we have a unit load and bending moment at point D. So these are the free body diagram for the 3 segments. Remember, when it comes to a frame, because this is a frame, this is not a beam. When it comes to frame, for the analysis of the frame, you need to separate different segments. Looking at the second classification of the frame, when it has internal pin, you need to disassemble your segment from the pin. So we did it, and we have 3 free body diagrams. I just put them inside the box so you can see them better. So we have 3 segments and so any question for this 3 body diagram? Clement, do you agree with this? The loading, because here is a pin, so we have shear force, sign convention, bending moment, unit load. Why we have only RE here? This is a, what support is this?
Tangential force only.
Is what?
It's a spring, so it's tangential force.
Yeah, it's just spring, so do not confuse it with the fixed support, right? So yeah, so we have only a tangent.
The 1 point load also be on the left side of
Yes,
D.
it means it is here, not here.
Okay.
So if you separate them, you just consider this line and separate right and left. So it makes difference. So in this case, the reaction at point E is equal to 1 Newton, if the unit is Newton. We are looking for RC. To answer the question from Clement, he said, this shear hinge is free to move vertically, but do you think MD has a value here? So it carries the moment, right? That moment has a reaction at this side. So basically we have a moment here, we calculate this moment, which is this one, and then we calculate RC, because we are targeting finding RC. So my recommendation is just do not do it based on your feeling, just follow the equation. So now I'll show you with the equation. We write this equilibrium equation for segment DE. We take a moment about point E, and then from here MD is 2L. I do not show you all the details, for example, sign convention, etc., because I think you understand. You take a moment about point E, then MD is 2L. Correct? And then when it comes to segment BCD, we take a moment about point B. From here, RC is MD divided by L, which is 2L divided by L, which is 2. We don't use unit. The unit could be Newton meter, etc. So the bending moment at point D, which is the shear hinge, is 2. For example, 2 Newton meter, etc. So we have a bending moment. And now we take a moment about point B here. We have MD, we find RC, so RC is 2. We found it. It's done. The answer for the question is 2. Because the question was asking about the height of influence line when you place a unit load at point D, and the answer is 2. So don't confuse them together. We are dealing with two things. The question is asking about the influence line for RC. And the unit load is just moving on this structure, but the question said when the unit load is right at the right side of D. So it could be confusing. You place the unit load at right side of D, you find RC. Because the sign convention is upward positive, and RC is downward because we already assume to be downward, and then it is +2. So we can say the amount of influence line for RC is -2. It means when you draw the line, it is down below x-axis. Our sign convention is positive. We are done with first part of the question. In the second part of the question, I'm asking you to help, because I just want to make sure you understand. Okay, I'm going to erase this part. Okay. Now, the question is asking, determine the height of influence line of E reaction or spring reaction. At point B. So you need to differentiate these variables. Spring reaction and point B. What are these two? Braden, can you explain?
So it wants the height of the influence line, based on the spring reaction,
Okay, where should I, Clement, I want to make sure you understand. Where should I place unit load?
Point B.
Mm-hmm. Yeah, I'm happy. Okay, so it means, yes, any question? So basically we have to place it at point B. And then what we need to find, Clement?
RD.
RE. Yeah, basically this one, the reaction in your spring. Yeah, that's it. That's it. So from here, this is not structure analysis, this is statics, because you place a unit load here and then you find RE, so it is just statics. But now, race. You never faced this issue when you passed statics. If I was the instructor, I told you, and I think I was the instructor in statics. The unit load is exactly at the axis of pin B. Where should I place it? Right side of B or left side of B? Because this is a question. What was your name?
Adrian?
Adrian. Because when you separate them, you have to decide. When it comes to shear hinge, he asked we place it at the right or left side. I said it makes difference, and then we have to place it at the right or left side. And the question told us to place it at the right side. But now the question doesn't tell us. It just says at point B, because it makes no difference. It is up to you. When you draw the free body diagram, you can place it at right side of B or left. Either. You will get the same answer when it comes to internal pin. Okay. So now I'm going to draw the free body diagram for each part. For the cantilever one, A, B, I place the unit load at the left side of B. It's up to me. And for the next part, C, B, D, what we have? We have VB here, according to the sign convention, RC here, moment, MD, E. E for spring. Any question for these internal forces? Clement, any question? Emma, any question? Okay. So basically we are looking for this. E for spring. I consider segment, the last segment, which is segment DE. And I asked Clement to take a moment about something. No. Clement, we are going to find E for spring. We have three equations, sigma fx, sigma fy, sigma m. Which one would you recommend? I mean, you can use three of them.
Fy.
Exactly, because this is vertical. Sigma Fy is 0. E for spring plus what? Clement.
Spring.
Yeah, E for spring is here. What? Do we have any vertical force acting on this segment race?
You do MD.
MD is not a vertical force.
No.
So we cannot include MD here. Do you agree? So when you don't have, then you don't have. So it's 0. That's it. Finished. It's 0. So the amount of spring force or tangent force is 0. I know Clement is trying to understand it based on his feeling, which is fine. You place a unit load here, the load goes here, but nothing will be transferred to this part in terms of feeling. Yeah, okay. So basically the amount of height of inference line for the spring is 0 when you place a unit load at point B. That's it. So we are done with the concept of inference line. We move forward with one more conceptual question, and then we are good to go for Mueller method. Okay. The last question from remember we are still using the tabulated method. There are plenty of questions in this way in the textbook. You just find the amount of inference line for different points and connect them by a straight line. And we have practiced it. Now we practice one more. This is FE exam. So you should be able to solve it within 1 minute. There is a beam sitting on support A. We have a roller support B. We have a pin at point C and a roller support at point D. L, the span. The question is asking you to draw influence line of, so what do you expect here, Adrian? It must be, for example, reaction for point A, reaction for point B. This is what we expect, right?
Yeah.
Because usually they say inference line for RA or RB or R reaction, or maybe the shear force at point C, internal force, it doesn't necessarily need to be reaction always. It could be internal shear force. Now the question is asking to draw inference line of RA plus RB plus RC. That's it. Draw it. And it gives you 4 choices. Now I don't draw it because FE exam has 4 choices. Where is the load? Alex, where is the load? We don't see any load here. When we want to draw inference line, basically we are not given a load. So we have to place a unit load, always, right? So where should I place the unit load? Anywhere. Remember, the unit load moves from A to D, and then the amount of variable, which is this one in this special question, will be changing. So if I place the unit load somewhere, this is the unit load, and the distance from A is x. It's a variable. So it could be any point on the beam. So how? If you use the tabulation or tabulated method, which we have been practicing so far, you need to place unit load at point A, at point B, at point C, at point D, and then you need to find these 3, add them together, and then connect those points together with a straight line, which is time consuming, right? So it means Adrian said, I put a unit load here, I find RA, then I find RB, then I find RC. 3 steps. Then he said, I put it here, again I find these 3. I put it here, I find these 3. So it is 12 steps, but you just have 1 minute during a FE exam. This is the way. This is reaction at point A, reaction at point B, reaction at point D. And your unit load is just somewhere, doesn't matter, somewhere on the B. And if I ask Clement which of the 3 equilibrium equations would you choose, previously he said sigma Fy. So now I'm recommending him to do the same. Okay, sigma Fy. Then Clement, do you agree that RA plus RB plus RC is 1? Yes? Yes. So 3 of them together are 1. But we don't know each of them. Maybe RA is 0.5, maybe this one is 0.3. We don't care. We know then they are together. The addition, the sum of RA, RB, RC is 1. And the question is actually asking for that. So the question is saying that if you have X and the vertical axis is the inference line. Again, to save the time, I just write IF, but it is wrong. You don't see that on the textbook. So don't do it. But now I just saved. Inference line for RA plus RB plus RC. How much is this, Clement? 1. When the unit load moves here, Selena, how much is it? 1. 1. Basically, it is just 1. It doesn't matter how much is X. So in this way, you can solve problem within 1 minute. That is the inference line. From A to D. A to D. Okay. So we are done with this, and now we move to next step, which is Mueller-Breslau principle. That is the main focus of our discussion. If you pay attention, it is easy. We will solve different problems. The variety of problems are higher than other chapters. Okay, I'm going to erase this. Any question, Tom? No?
Should it be RD the whole time, or is it RC?
Say again?
Should it be RD? The
Yes, you're right. This is RD. The last one is RD. Yes?
Because it's in almost all of them.
Yes. Yes. RABD.
Okay.
Yes. Okay. Thank you. I write the principle of Mueller-Breslau in different steps. Usually you don't see these steps. I mean, if you read the textbook, it is written in a statement, but I break it down into different steps. So the person who proposed is Mr. Mueller-Breslau principle. So it is famous to Mueller principle. So the scientist who proposed this principle is called Mr. Mueller-Breslau. This principle is the way we draw inference line. So basically you don't need to calculate all of those numbers. It qualitatively helps you to draw the inference line for many of these structures. It has different steps. Number one, Step number 1, remove the related variable. Remove the variable. You may not understand it, but when we practice it with questions, then you understand. And then replace it with proper joint or support. Step 2, apply a unit displacement or rotation. Corresponding to the removed variable. And find the deflected shape of structure. The deflected shape of structure that you found is actually inference line. So now we practice it on a simple question to understand these steps. We are going to use Muller method to draw the inference line. Draw inference line for support reaction at point A, vertically, support reaction at point B. There is a beam support reaction A and B. So we start with a simple question. Okay, I'll give you time to take a note and then we solve it. First step, remove the variable. What is the variable, Alex? These are the variables. Sometimes the question says RA, sometimes RB, sometimes moment. So we start with the first one. We remove it. Okay, if you remove R, the reaction at point A, basically you end up with this. So point A is free and you don't have any variable or reaction. Okay, this is step number 1. Yes?
So just a quick, when you remove the variables, you only remove one at a time? Is that how?
Yes, only that variable.
Okay, so since we have two, then later on we'll keep.
Yeah,
names.
so maybe I should simplify the question to avoid any. Basically, the question is asking to draw inference line for RA bar.
Oh, okay.
That's it. And then for another question later we discuss. So we are just going to draw inference line for RA bar. A single question. So we remove the variable. Next, replace it with a proper joint or support. How? When you remove this, basically point A is free. So you don't need to replace it with anything. But sometimes when internally you remove a variable, you have to change that convention. Later you will see. But here we don't need to do anything because point A is free. Now, second step, apply a unit displacement or rotation corresponding to the removed variable. Alex, the removed variable was a horizontal or a vertical reaction or a moment. Which one?
That it was a pen, right? So,
Roller.
oh, it was a roller. Then it's.
Yeah, but was it a vertical reaction or horizontal reaction or a moment? Originally, what was it when I erased it?
Oh, it's a.
It was a vertical reaction, right? It says apply a unit displacement or rotation corresponding to the removed variable. And Alex said it was a vertical one. So now I must apply a unit displacement or rotation. Which one? I must apply displacement because it wasn't a moment. So now I apply a unit displacement. It means I hold point A with my hand and I just move it to a place upward with a unit displacement. I don't rotate it because it wasn't a moment. It was a reaction, it was vertical, so correspond to that vertical reaction, I just move it upward. Why do I move it upward, Race? Because the sign convention,
Support reaction.
yeah, because the sign, yes, but the sign convention is positive upward, so I move it upward. Okay, next step. Find the deflected shape of the structure. So it means when Alex holds point A with her hand and just lift it up, the entire structure will be deformed in this way. Do you agree? This is deflected shape. And that is the answer. So the green color is the inference line. This was Mueller method. So in the exam, of course, you need to redraw it like this. You say this is X. Then you need to say, okay, this is RAY, and then just redraw it. And then this is unit, that's it. This was a simple question. And remember, inference line for determinate structure is always linear. That's why the green line is just a line, because this structure is determinate. Next question. Any question? So we are going to practice these steps. These are 2 steps, but they have interpretation. Yes, Race.
On the exam, would you have to put B on the influence line so that you knew where it's
You mean here? Yeah, basically, this is point A, this is point B. This was this, but yes, location of point A, B, C. Yeah. I'm going to erase this part because I want to keep these steps. Draw the inference line. But the second part of the question was about the second part of the question said RBY. Vertical reaction at point B. So the same beam, A is a roller, B is a pin. Now, we'll repeat the same process. First step, the question is about RBY. To avoid any confusion, first I show you that variable because this is RBY. Second step, remove the variable. Okay, remove it. I just erase it. Replace it with a proper support or whatever. Point B is free, we don't need to replace it with anything. And apply a unit displacement. Okay, again, we grab point B, move it upward, and then we connect A to B. Basically, this is deflected shape. Deflected shape. And this is the answer. So you need to redraw it. Point A, point B. Inference line is for R, B vertical. That's it. You use Muller method. Next, I'm going to erase this and go for next problem. We will practice this Muller method for many problems. We have a cantilever beam from A to B. Draw inference line for AY. Now I intentionally write both of them because it was a question from Alex. And MA. Basically, there are two questions combined together. So it means first you need to draw it for AY, forget about MA, just erase it. And then second part of the question, draw inference line for MA. So there are basically two questions here. The length from A to B is just L. First step, I just want to show you the variable. This is beam from A to B. The variable is point B is originally free. Now, when you look at reaction A, you have horizontal reaction, AX, you have vertical reaction, AY, you have bending moment. But you just need to remove one of them. Which one shall we remove? AY, right? So if I remove AY, I just cross line it like this, and I just erase it so we don't have it. Now, it says replace it with a support or joint. The reason it is saying is because now you have AX and you have M at point A. So you have to replace it with a proper support. What is that support which carries the horizontal reaction and moment but doesn't carry any vertical reaction? I think Kelemen knows the answer. Because it was your question. I'm going to place this reaction here. Do you agree with that? Horizontally, it has a reaction. In terms of moment, it has a resistance. Vertically, it doesn't have any reaction. You said that, right? So this is a proper one. When I say proper support, it means this one. Replace it with a proper support because you already removed one of the variables. That's it. Any question? Now we are done with first step. Second step. Apply a unit displacement or rotation corresponded to the remove variable. The remove variable was AY. So in the same, when it says corresponding, it means in the same direction. So I must apply a unit displacement vertically at point A. So it means Alex must hold point A and lift it upward with one unit. And then she must imagine the deflected shape. This is kind of imagination. How would it deform?
Or just all shipped out?
So point A ship up. What about point B?
All of it shipped
Yes, yes. So this is the answer. The red color is the inference line. So in the exam, you just redraw it. You say this is X. The vertical one is the inference line for A, Y. And then the red colored line is the inference line. That's it. Why do we move it upward? Because the sign convention said upward is important, upward is positive. But remember, this is just a sign convention. If you see a textbook and you see this line is just below x-axis, that is just correct. It's not about the sign, it's about the magnitude. So when we say sign convention, it means this is just an assumption. We assume the positive side is upward, that's it. Yes?
Do we need to write like 1 on the actual map?
Yes. You should say this is 1. Yeah. Next part. So now Alex just removes this AY to avoid any confusion, and then she goes for MA. So we resolve this problem for MA. Okay. MA. So this is the beam from A to B. The reactions are AY, AX, MA. Which variable shall we remove? Which one? Yes, moment at point A. Okay, we just remove it. And then it says, replace it with a proper support. So there must be a support that, what is that support?
Pin?
Yes, because it's a pin, yeah. So basically, Braden said, replace it with a pin. Clement, you look weirdly something. Do you agree with this? Yeah, because it doesn't have moment, but it has horizontal and vertical reaction, so it's a pin support. So when we say replace it with a proper support, this is what we mean. Sometimes you need to replace it with a joint when it is internal joint. Later you will see. Step number 2, apply a unit displacement. Not, okay, now my question is, displacement or rotation? Which one? Rotate. Why?
Because it was solving for the rotation. And then
Yeah, because it's a moment. Moment is about rotation. So now apply a rotation at point A. I grab this and I apply in this way. So basically, this is the rotation, but I want to draw it better. So the red color is the answer. I just rotate it with a unit amount of rotation. There are a couple of important things here. First of all, why do I rotate it clockwise? It is sign convention. You can do it counterclockwise. The only difference is the sign, but the magnitude is the same. And basically, we use this sign convention. Another thing is, when we say unit rotation, what do we mean by unit rotation? It means slope. The slope is unit. This is one of the interpretations of the Mueller steps. The slope. Slope means if this is theta Tangent of theta is the slope. Do you agree, Adrian? Tangent of theta is the slope. And it must be unit. So if this is L, this is L. And basically, theta is 45 degrees. Unit slope. And then you redraw it in the exam. You say this is X, this is moment at point A, The textbook doesn't discuss the angle. When you look at the textbook, you don't see this angle 45. Because textbook doesn't want to go through more details. It's not required. So the slope is unit. It means tangent of theta is 1. It means this is 45. It means this is L, this is L. That's it. Inference line for MA. And the reason we turn it in this direction is because clockwise, we use clockwise as the positive sign. There is another reason for this sign convention. I just want to clarify on that. Basically, you consider epsilon distance from point A, and you just cut it at point with the epsilon distance. So basically what you have is this one. And then you apply the sign convention in this way. The left side is very small, so we don't see that. The right side is the one that you turn, is this AB, and then you turn it in this way. That is another reason. So forget about this small part. So this part, this sign convention, rotate it clockwise, and then you see. There are a lot of interpretation. I mean, basically, these are interpretation for Mueller method.